talking about the basics of graph theory. Uh, so first of all, let's talk about what a graph looks like. So in a graph, you have something known as a vertex and you have something known as an edge. Okay, so in a graph, you have some vertices and you have some edges which are connecting two vertices together. Okay, and edges can be, say, directed. Like for example, here this is an undirected edge, and this is a directed. This is directed. What directed and undirected really means is, uh, so undirected edge, for example, it's say there are two cities. There are two cities, and there is a road between these two cities. This road can be traveled in either direction. You can go from city A to city B, or you can go from city B to city A. Directed edge, um, let's say you go from, okay, so I cannot think of an example, but like the idea is that you can go from A to B, but then you cannot go back from B to A. Okay, so A to B,
Something like a one-way road.
yeah, it's a one-way road. Yeah, yeah, you're right. It's a one-way road. So yeah, you can go from A to B, but you cannot go from B to A. Uh, and these edges themselves may have weights, or even the vertices themselves may have weights. Uh, what a weight signifies depends on context. I mean, it depends on the problem. Usually, when we say weights, we are interpreting them as lengths. So, you have probably heard of the shortest path problem. So, like, you have a graph where each vertex is a city, let's say, and each edge is a road between two cities, and each road has some length which is given by these edge weights, and then you just have to find the shortest distance between city A and city B. So it does not always have to mean path length, though. It can be interpreted in various ways depending on context. Uh, so the next thing that we are going to talk about is some terminology, a list of terms that you should know uh, when you're doing graph theory, because it will help you, because usually uh, problem statements for graph theory, I mean, for problem statements for graph problems, we usually contain these terms, and you need to be able to understand what these terms mean. So uh, okay, so a graph is composed of some vertices, which, I mean, it's not always they will call it vertices, they can also call it by nodes. Both vertices and nodes mean the same thing, they're just synonyms. Vertices and edges, which we saw previously, what a vertex and what an edge is. The problem can call it anything similar, like it can be, as I said, you can have city, road intersection, room, corridor, but point is that you can always model it like a graph. Basically, you just have some places and you have some connections between those places. That's basically the thing. Vertices or edges may have weights. As I said, the meaning of what weight is depends on problem. And I give you an example also, like shortest path problem. Again, as we saw before, edges may be directed or undirected. Directed edges are, like someone correctly said, it's kind of like a one-way road. You can only travel it from A to B, but you cannot travel it in the reverse direction. But in undirected, there is no such restriction. You can go in either direction. The next thing is, are these terms called degree, in degree, and out degree. So In an undirected graph, the degree of a vertex is the number of edges that is incident to it. So going back to a previous example, uh, let's see what the degrees of these vertices are. So for say this vertex, the number of edges that are incident to it are this one and this one. So there are two edges. So the degree of one is 2. Similarly, degree of this vertex 5 is 1, 2, 3. The degree of vertex 0 is 1, 2, 3. Uh, 4 is 1, 2, 3, 4. Then 2 is 2 and 3 is 1. So these are the degrees of the vertices. Degree is how many edges are incident to this vertex. For an undirected graph, undirected graph means where all the edges are undirected. And directed graph means where all the edges are directed. So this is an undirected graph, and this is a directed graph. Uh, in directed graph, we don't just have the concept of degree, but we have two separate concepts, which are in degree and out degree. So in a directed graph, the in degree is the number of edges that end at that vertex, and the out degree is the number of edges that start at that vertex. So in this graph, uh, we have say the out degree of 1 is 2. So there are two edges that start at 1. One is starting at 1 and ending at 5, and one is starting at 1 and ending at 4. So the out degree for 1 is 2, but the in degree is 0 because there are no vertices that are entering, that is ending at 1. Uh, by comparison, 5, this vertex has an out degree of 0 because there are no edges which are starting at 5 and ending at something else, but its in degree is 3 because there are three edges, one starting from 1 and ending at 5, 4, 5, and then from 0 to 5. Okay. So similarly, you can list out the in degrees and out degrees of the remaining vertices. So this one has say out degree 1 to 5, this one, and then in degree is 3. And likewise, you can write out this one as well. This one is okay. So this is what out degree and in degree means. Uh, I hope everyone understood until this point. Yeah, so the next thing we are going to talk about is are these things called loops and multi-edges. So a loop is an edge that starts and ends at the same vertex. So say you have some graph that is like this, say vertex 1, 2, 3. So a loop is an edge that goes like this. It starts and ends at the same vertex. Uh, for directed graph, it is pretty much the same. For directed graph, say you have something like this, uh, then you can have an edge like this. This is both of these are loops. One is just undirected and one is directed. But it doesn't matter because they are both starting and ending at the same vertex. Okay, this thing is called a loop. And the next thing that we're doing that is there is multi-edge. So usually there is only one edge connecting two vertices. So you will see in the graphs that we looked at, between 1 and 4, there was only, okay, between 1 and 4, there was only one edge. Okay. So here also between 1 and, I mean, here we can also have, say, an edge from 4 to 1 that would count as a separate edge. So okay, let me just redraw it. So uh, you can have something like this. Okay. So this is fine because we have only one edge between any two vertices. And here in this directed graph, we can have something like this, and then we can also have say like this. So one edge is going from 1 to 3. and one edge is going from 3 to 1. These two are different edges because, I mean, in a directed graph, you also have to care about the direction of the edge. It's like here we don't have a direction, so it doesn't matter. So, but here it does matter because a direction is associated. But the point is that in some kinds of graphs, you can also have this. So usually you will find that it also has some kind of weight, like this has say a weight of -2, this has weight of 1, this has weight of 3, and this has weight of 4. So these edges go between the same two vertices. Okay, so these they go between the same two vertices, but they are not the same edge. In this case, we say that the graph has multi-edges. Okay, so you can think about it as there being two different roads from city A to city B, two different roads. Okay, so for directed graph also it is similar. It's just that you extend it to like now these two edges are the same, or say you have like this, then these two edges are the same. So this is a case of multi edges. Usually you will find that problems do not have loops or multi edges, but sometimes it is possible. Like so in some problems you do have loops and multi edges. In the case that you have no loops or multi edges and the graph is undirected, that kind of graph is called a simple graph. Sometimes you'll find instead of saying that the graph has no loops or multi-edges, in the problem statement, they'll just write you have a simple graph. So this is what it means. No loops or multi-edges. Now we have a simple cycle. So a cycle, a set of vertices is set to form a simple cycle when you start walking from a vertex and then at the end you end up at the same vertex. But you have not traveled the same vertex or edge twice, except start vertex. So, for example, in this graph, this thing is a cycle from 1 to 3. So, you start walking from 1, you go to say 3. So, after that, you go to 2, and then from 2, you go back to 1. So, you have just completed a tour of this entire of these three vertices and you have ended back at the same vertex. So this is called a cycle. But the important point is that you cannot repeat any edges or vertices. So if say if I went from, oh, if I go from 1 to 3 and then from 3 to 1, that's not a cycle because we have traversed the same edge twice. Okay, like of course, we have gone from the start vertex and ended back up at the start vertex, but we have repeated this edge. That is not allowed. If all the edges and vertices are distinct, like here, in that case, it's called a cycle. So you can have cycle of size of length 3, cycle of length 4. So this is all in undirected graph I'm drawing. So like this cycle of length 5. Then you can have some more vertices. You can have cycle of length 5 and cycle of length 4. And then here also, if you see like this, if we walk, then we'll have some cycle of length, say 1, 2, 3, 4, 5, 6, 7, cycle of length 7. So yeah. Uh, mm, okay, so this is the concept in undirected graph. In directed graph, it is similar, but all of your edges have to be directed in the same way. So it basically means so this is a cycle because you go from 1 to so 1 2 3 1 to 2 2 to 3 and 3 to 1. This on the other hand is not a cycle. Say this and this 3 2. So you can start from 2 go to 1, then from 1 to 3, but then you cannot travel from 3 to 2 because the edge is opposite in the opposite way. So here there is no cycle. So yeah, that is the concept of cycle in directed and undirected graph. So example of size 4 directed cycle is something like this. Uh, then let's say you can have another cycle attached to it. So you have a cycle of length 3 here and a cycle of length 4 here. Okay. Now, uh, directed acyclic graph. Uh, this particular thing is also important. This particular thing because a directed acyclic graph has some interesting properties. Uh, in particular, you can actually do dynamic programming on these graphs, which is interesting, and that is because there is no cyclic dependency. We'll talk more about directed acyclic graphs in a future class where we'll talk about things like topological sorting and how to do the dynamic programming problems like longest path. But yeah, so in a directed acyclic graph, there is no edge. So this thing right here is a DAG. This thing is a directed acyclic graph because there is no cycle in this graph. You cannot, start from a vertex and end up at the same vertex in any way. Right. Uh, okay, so the next thing we're going to talk about is a walk. So a walk is a sequence of vertices such that any two adjacent vertices are connected by an edge. The concept of walk does not make any restrictions on whether I mean, it's not saying that you cannot repeat a vertex or an edge. In walk, you can absolutely repeat a vertex or an edge any number of times you want. So for example, in say, let's draw this graph, I can go from like this, let's say. So say I can do like this 1, 3, 2, 1, 4, 3, then 1, 2, like this. I can just keep going. Uh, so like this is a sequence of vertices where every two adjacent vertices, these two vertices, they are all connected by an edge in the graph, as you can see. 1, 2, 3 is connected by an edge, 3, 2, 2 is connected by an edge. And like we can, as you can see, we can repeat vertices any number of times we want. We can even repeat the same edge as many number of times as we want. 1, 2, 3, 3, 2, 1. We traverse the same edge twice. So it's a walk, and the concept of walk is actually it's not that common in problems, but there are some problems where you are asked to find, say, a walk of length k, problems like that. Uh, so in directed graphs, the concept is similar. Again, in directed graphs, since you have like one-way edges, you cannot like if say I made this same graph but directed, so I have something like this, like this, like this, and like this. Then here also you can again take some walk. You can go from one, 1, 2, 3, 4. You can go from 1 to 2 to 3 to 1, and then you're kind of stuck. Okay, so then 2 to 3 to 4 to 1 to 3. No, not 1 to 3. Okay, so like there are very limited possibilities for a walk here, but I hope you get the idea. Uh, the other thing is, which is more important actually, path. Path is a walk without repeated vertices and edges. Now, this concept of finding a path, you will come across a lot. Like, I mean, you just came across it before. Shortest path problem. Wait, yeah, shortest path problem, not shortest walk problem. So in path, you cannot repeat vertices or edges. So this thing is no longer allowed. So you walk from, so if you have, say, some complicated graph like this looks like this, okay. So you can walk from, you can take a path, so like this, and then end up here at this vertex. So you go from here to here, here to here, here to here, here to here, here to here. So here you notice that we do not repeat any vertex or edge, and that is not allowed. No vertex or edge must be repeated. Uh, you will, I mean, path is very common. They'll ask you to find, say, find a path which repeats. Okay, no. Uh, find, say, shortest path. That's one example. Find two paths so that the number of common edges in them is odd. Just random way. So if I take from, if I walk from, if I walk from here to here, if I walk from here to here, this is an example of two paths whose number of common edges is odd. In this case, it's only this edge is common between the two paths. So anyway, you will encounter path a lot, a lot. Okay. Uh, Now the next thing is a connected component. So a connected component is a maximal subgraph of the given undirected graph such that there is always a path between two vertices in the subgraph. This definition will not work well for directed graphs, and I you should think why after I introduce what is a connected component. This connected component definition is only for undirected graphs. So okay, so if I can have a graph, I'm just drawing a box here. So this graph has, let's say we have a graph like this, like this. Okay, and say we have like this also. So I am not going to define subgraph very rigorously, but uh, intuitively speaking, is just a smaller part of a graph, subgraph, smaller part of a graph. So the idea is that you take the largest subgraph such that there is a path between any two vertices in this graph. Okay, so this is one connected component. This square thing is one connected component because there is always a path from, say, here to here, 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 let's say. But if we take, say, this thing and this thing right here, these two things do not form a connected component because there is no path from, say, this vertex to this vertex, right? So this graph that I've given here has four connected components. This is one, this is one, this is one, and this is one. There are efficient ways to find the connected components of a graph using either depth first search or breadth first search. Graph traversals we'll talk about in this class if we have time, and if not, then we'll talk about it in the next class. So uh, that's connected components. Again, very important concept you should remember. And connected graph is a graph which has only one connected component. So basically, uh, this graph is a connected graph because there is a path between any two vertices in this graph, right? So you can take a path from like from 1, 2, 3. If you want to go, you can go like this, you can go. So any two vertices you pick, there will always be a way to go from that vertex to the other vertex. So this graph has only one connected component. Any questions up to this point? If you want me to again explain some definition or any anything. Okay, so no questions? No questions? Okay, fine. We will move to the next slide then. Uh, this thing, the next thing we are going to talk about is strongly connected component. Okay. Uh, so in directed graphs, you do not have a concept of connected components. Instead, you have a concept of strongly connected components. And what is a strongly connected component? A strongly connected component is a maximal subgraph of a directed graph such that it is possible to start from any vertex in it and end in any vertex in it. It's similar to the definition for connected component. A maximal subgraph of the given undirected graph says that there's always a path between two vertices in the subgraph. But you have to notice that if I give a connected component in a graph, then if I direct some of its edges, then you can no longer say that this entire connected component also forms a connected component in the directed graph, right? So uh, a directed graph can be decomposed into strongly connected components, just like for say undirected graphs, you can make connected components out of them. You can also make um, strongly connected components out of directed graphs. This graph I gave as an example, this actually has, I mean, each vertex by itself forms a strongly connected component, but there are better examples. For example, let's say I give you a graph that looks like this. Okay, so say I direct it like this. So now there are two connected components in this graph. One is this thing. This is a strongly connected component, then there's a separate strongly connected component. Okay, so uh, to decompose a directed graph into strongly connected components is not as simple as finding connected components in an undirected graph. For connected components in an undirected graph, you can just run DFS or BFS and you will get a very simple way to do it. But for strongly connected components, the algorithms are kind of more complicated and they have names. So two algorithms for finding strongly connected components are Tarjan's algorithm and Kosaraju's algorithm. We'll talk about those in another class. Okay. So, uh, okay. So like consider, I mean, okay, you get the point. Like if I gave you this thing, this is a connected component, but then if I direct this edge, can you still call it a connected component? You can't, right? Because you can go from you can go from 1 to 2, but you cannot go from 2 to 1. So it does not satisfy the condition of connected component. Instead, the two connected components, I mean, two strongly connected components are this and this, size 1. We'll discuss strongly connected component in more detail in a later class. It's a little advanced concept that you won't be seeing in diff 3 or at least lower diff 2. But yeah, uh, complete graph. So a complete graph is simply a graph which has all possible edges. Okay, so if I give you a graph of size 5, let's say, so in that case, a complete graph of size 5 would have an edge between every pair of different vertices. So yeah, from here to here, like like this, then so like yeah, all the it's a regular pentagon with all of its diagonals. So yeah, that's a complete graph. Undirected graph says that there's an edge between every pair of different vertices. More examples of complete graphs. This is a complete graph of size 4, size 3, uh, size 2, size 5, and size 6. You can imagine it's just going to be imagine a regular hexagon with all of its diagonals. Okay. Uh, Complete graph is also important, and the next thing is very important. We'll have a whole separate class, I think, on this particular thing, and that is tree. Okay, a tree is a connected undirected graph that has no cycles. So like, uh, note that a tree is not the same as directed acyclic graph. I mean, as I showed you, like if this is a DAG, but and then if you remove the directions of all its edges, it just becomes a triangle. But that is a cycle in undirected case. So DAG and tree are not the same, though. So a tree, a tree is a DAG. I mean, if you have a tree and then you direct some of its edges, you give some of its edges directions, then it becomes a DAG. But a DAG is not always a tree. Well, in this case, you can call it a directed tree since you're directing its edges. So an example of a tree is like, let's say, like this. You've probably seen this kind of structure before. So this is a tree. So a connected undirected graph with no cycles. Note that a tree is connected also. So a tree has exactly n minus 1 edges. For those of you who do not find this fact obvious, just think about it a bit. If you have n vertices, you will always have n minus 1 edges in a tree. So in this tree, we have 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So 10 vertices and 9 edges. So this is true for any tree. If it's not obvious to you, I encourage you to think about it and prove it. And a forest is a collection of trees. So, I mean, that is very simple, very nice naming also. You have a bunch of trees. So, like this. This is a forest, you can say. This thing. So, a tree is one connected component, but a forest is several connected components, and each connected component is a tree. That ends the list of terminology here, but the list of terminology actually required in graph problems is vast, and you will be coming across many more terms uh, in the following sessions. But this is just a small list to get you started to understanding graph problems. Okay, so any questions up to here? No questions?
No.
Okay, so in that case, I'll just move on to the next slide. Okay, so now we'll start getting into a little bit of uh, how to actually deal with graphs and problems. So the first step to dealing with a graph problem, of course, you need to be able to represent the graph somehow. We have drawn it using our using on we have drawn it on paper, let's say, but now how to actually represent it in memory? Okay, how to represent it in a computer? So there are two main ways to do this. The one of them is called adjacency matrix and the other one is called adjacency list. So two nodes in a graph are called adjacent if they are directly connected by an edge. So in this graph, say 1 and 5 are adjacent, 1 and 4 are adjacent, 4 and 5 are adjacent. 4 and 0 are adjacent, but 1 and 0 are not adjacent because 1 and 0 are not connected directly by an edge like this. Okay, so uh, the more common way to represent a graph is adjacency list. This is more common way. But adjacency matrix is also used in several cases. So for example, if you have heard of it, there is this algorithm called Floyd-Warshall algorithm. So in this Floyd-Warshall algorithm, we use this adjacency matrix, but instead of like it's a little modified adjacency matrix. It's not the way I'm going to define it here. It's a little bit different. So, but the idea is the same. Floyd-Warshall, or say in say a graph, you want to find number of walks of length k. So this problem where I give you a graph and ask you how many ways are there to walk from some vertex to some other vertex in exactly k number of steps. And surprisingly, this problem is something that can be solved using matrix exponentiation. which you have previously learned. So matrix exponentiation has other uses than just linear recurrences. Uh, so yeah, it's maybe we'll talk about this later on, but you can solve this problem of counting walks of length k using matrix exponentiation, and that in that place you can use the adjacency matrix, but most of the time you'll be using adjacency list. Okay, so what exactly is adjacency matrix? So in the adjacency matrix representation, we have a matrix of size n cross n, where the I comma jth term is 1 if we can go from I to j directly, and in other words, if I and j are adjacent, and 0 if we cannot. For undirected graphs, the adjacency matrix is symmetric. The meaning of symmetric is Gij is equals to Ggi, and obviously that is because if 1 and 5 is connected, then 5 and 1 is also connected since the edge is undirected. It's a two-way road. Okay, but it's not always true in a directed graph because again, if I give an example of like this, you can go from 1 to 2, but you cannot go from 2 to 1. In this case, G12 will be 1, but G21 is equals to 0. So these two are not equal. Are not equal. But if it was undirected, then G12 is 1 and G21 is also 1. So these two are equal. So we want to find the adjacency matrix of the graph that we are given here. So let's just draw this. So 1, 2, 3, 4, 5, 4, 5. So I want you to work out what is the adjacency matrix of this graph using the definition that I've given. Okay. So if anyone is willing to try and tell me what is the adjacency graph, please go ahead. And adjacency matrix of this graph. I'll fill in a few entries. So 1 to 5 is obviously 1. 5 to 1 is also 1. 1 to 4 is 1. Uh, then 4 to 1 is 1. But it's not connected to anything else. It's not directly connected to 0 or 2 or 3 by an edge. So these will be 0. Obviously, 1 is not connected to 1 itself since we have no loops in this graph. So is anyone willing to tell me what the remaining entries of this matrix are?
2, 4 and 2, 3 will be 1, as well as 4, 2 and 3, 2.
Yeah. 2, 3 is 1.
2,
4,
4.
2. Okay, 4, 2 is 1. That also makes 2, 4, 1. Because undirected edge, and that makes 3, 2 also 1. Then
Others will be 0 in 2.
will be 0. Yeah, that's true. Then for 3, okay, 3 remaining.
Remaining will be 0.
Yeah, so 0. And this one?
4, 5 and 5, 4 will be 1.
Yeah, that's correct. So yeah, this is the adjacency matrix of the graph. Yeah, this, you have done it correctly. I think. Yeah, you have done it correctly. 2, 3, 4. Okay, yeah. I have made a mistake. The numbering starts from 0, so there should be another one. There should be another entry right here. There should be a 0. Uh, my mistake. But I guess you get the concept, so just 4, 5. Oops, what did I do? Hold up. Wait, how to consume? Oh, there we go. Uh, yeah, I made a slight mistake, so my bad. But you get the idea. This is 0. Uh, this is no wait. Everything should be moved down. Oh no, this graph is a mess. This is a mess. But I think I hope you get the idea. Okay, I'm just going to. Okay, this kind of a mess to fix. Uh, Fix this. Zeros. Zeros, 1 1. Also 1. These four are 0. Yeah. Okay. Now this is correct. Okay. Uh, so yeah, I think everyone gets the idea of adjacency matrix, and we'll look at the code for this in just a bit. But before that, we'll talk about the adjacency list representation. Okay, so in adjacency list
I have a
representation,
doubt.
yeah, what?
If any of the numbers are missing, like if we don't have 3 but we have 6, then what is to be done?
So for example, you have a graph like say that is numbered like 1, 2, then 4 and 5, like this. I mean,
Yes.
okay. Okay, in problems, you will uh, pretty much always you will be given a graph that is numbered from 1 to n. There is no node that is going to be missing. And even if it does not appear in the list of edges, we assume that is not connected to anything. So it's like this. No node will ever be missing in a problem. Okay, you will always have all nodes from 1 to n.
Okay.
Okay, yeah, it's yeah, you never have a missing node anyway. Yes, sir. Adjacency list representation. For each vertex, we will maintain a list of vertices that are adjacent to it. Okay, so let me just go back and talk a bit about the memory and time complexity of this. So, I think it should be fairly obvious that the memory complexity of this is going to be, well, O of n squared, because we are storing an uh, n cross n matrix. This is the memory. Okay. And the time complexity is, well, first of all, it's O of n squared because, well, you have to initialize the whole matrix. I mean, you have to create the whole matrix of n into n terms first. And on top of that, it will take plus m to initialize it, where m is number of edges. This is the time complexity of this. Yeah. Uh, I mean, of course, as you can see, this is pretty bad. O of n square plus m is, I mean, the n square term itself is bad because in most problems you will have n less than equals to something like 10 to the power 5. But in adjacency list, you will see that it's the time complexity is much smaller. So we want to find the adjacency list representation of the graph on the right. Again, we maintain a list of vertices that are adjacent to it for each vertex. So if I just write it out here, 0, 1, 2, 3, 4, 5. So each of these is a list of its own. So I'll just write out the list for 0. For 0, 0 is adjacent to 4, 5, and 2. Wait, I made another mistake. This will be 1. Yeah. So 0 is adjacent to 2, 4, and 5. So its list, its corresponding adjacency list will be 2, 4, 5. So what will be the list for the remaining ones?
1 4 5.
4, 5. Yeah.
We'll have 3 4 0 4 0 3 4.
Yeah.
3 will have 2 0 1 2 5.
0, 1, yeah. You don't always have to say them in sorted order. There is no restriction like that. You can say it in any order you want. By the way.
5 will have 0 1 4.
0, 1, 4. Yeah, that's correct. This is the adjacency list representation. And if we talk about the memory and like time complexity of this, the memory complexity, I think it's okay. So the memory complexity will be, well, O of n, first of all, because you have to make n lists. So one for each vertex, so n lists there. And then on top of that, for each list, you will have some number of vertices. Now, the important thing to note here is that overall, if you look at it, uh, each vertex is going to appear in some list to the number of, okay, sir. Vertex, if you're talking about vertex I will appear in degree of I lists, because every node that vertex I, say vertex 4 is adjacent to, every one of those will have 4 in its list, right? So it will appear in exactly degree I lists. So the total, the sum over all, so if we sum it over all vertices, we will get this sum total, because it's basically talking about the edges. So yeah, uh, yeah. So in other words, you can look at it as like if you look at any vertex I, the number of entries in its list will be equals to the degree of that vertex. So if we sum over the degrees of all vertices, it actually turns out that we will get just 2m. So where m is the number of edges. So it ends up being of n plus m. Now, this specific result, that the sum over all vertices, the sum of degrees over all vertices is 2m. This is something known as the handshaking lemma. Uh, so, I mean, this is a fairly easy to prove result. If anyone wants to give me a quick proof of it right now, please feel free to do it right now. Otherwise, if no one can do it, then I'll just ask you to think about it for yourselves. So, does anyone want to try and prove why this is true?
For each node, we are counting each edge one time, and then in all, we are counting each edge 2 times.
Perfect. Yeah, that's the explanation. For each edge has two nodes on each end of it. So that particular edge will be counted twice only. Okay, so once in the list of this and
Could
once in
you
the list of
explain it
that.
again? Like my net was not working.
Which part?
Like theory.
Huh?
Actually, could you explain this part once again? I couldn't hear you. My net was not working properly.
No, I mean like this handshaking lemma or the adjacency list?
No, no,
The
no.
mem
From the total memory part.
Okay, total memory. Okay, so that is just O of n plus m, because this term is because for each vertex you have to make a list. So you have n vertices, so you'll have n lists. And this m part comes from this handshaking lemma. So for each list, you will have some number of vertices in its list, and the total size of this list will be equal to degree of that vertex. So overall, in total, you will have this quantity as the number of elements in the list overall, and that turns out to be just linear in M. So you will just require n plus m for storing each list. So that's the memory complexity, and the time complexity is also the same. It's going to be O of n to make the n lists, and then plus m for each edge that you add. Okay, you get it?
Okay.
Yeah. So this is way better than the adjacency matrix representation, which was n square plus m. this is O of n plus m, which makes the constraint of n less than equals to n to the power 5 much more manageable. And you will see that, I mean, everything becomes much easier this way. Even DFS, BFS you can implement very easily. Okay, so uh, okay, so now let's just take a look at how to implement it in code. Of course, this code is in C++ and it uses STL. I hope no one has any problems understanding C++ code right now. So in this is the code for adjacency matrix. Adjacency matrix, and this is the code for adjacency list. Okay, so let's just understand this code. So this line right here, this creates our n cross n matrix as a vector. Okay, I mean, you can use an array also if you want, fixed size array. It's up to you, but you get the point. You just need to have a two-dimensional array or vector or whatever you want. Okay, and then we just go over each edge and we input the edge. Usually you will be given edges in the form, you'll be given it something like UV, two space separated integers, which means that U and V are connected in the graph. So if it's a directed graph, you will just make GUV equals 1. Well, because well, if you're given U comma V, it usually means that U goes to V if it's directed. Uh, but if it is undirected, you will notice that V is also adjacent to U because, well, it's a two-way road, right? So in that case, you will also have to make G view equals 1. In problems, usually they will only give you U comma V, and if it's undirected, they will not additionally give V comma U also. Was someone saying something? Okay. Oh yeah, by the way, right here you want to initialize this entirely with zeros first. Uh, this so that you don't have to go over them again and set anything that was not in the list of where edges, you make it well, 0 because it's not in the list of edges. But yeah, that's the idea. So, mm, okay. Oh yeah, one more thing. Usually you will be given the input as one index. So if you'll probably be given as 1, 2, 3, and you will not be given it as 0, 1, 2. So make sure to just add a small number, say 1 or 5, anything to your matrix so that you don't end up doing out of bounds access when they give something on n, because remember array vectors are zero indexed, arrays vectors they're zero indexed. So just you should remember this. uh Now adjacency list, it's similar, I guess. Here we have again a vector of vectors, but here we are not filling the list with anything. So just so in this case we had uh lists. Okay, wait. Uh, so like we had something like 0, then 0, 0, 0, 1, 0, 0, 0, and then we have 2, 0, 0, 0. So I mean, obviously you can see this takes 3 into 3 operations to build. Uh, in this case, you will notice that we have kept it empty, right? So for each vector, we have kept it empty. So 0 is just empty, 1 is also just empty, and 2 is also just empty. So it takes no time to create these lists. So it just ends up being O of n time because uh, now, I mean, wait, do you guys hear some background noise? Like, can, is there some background noise with it? I'm audible. Uh, can someone
Sorry.
just there's no background noise, right? Oh, okay, okay.
No, it's there.
Okay, okay. Just someone is playing music in my neighborhood. Anyway, uh, okay, so here we just created this as I said, O of n, and then for each edge, we will input the edge, and then we do this line G U and pushback V. So from the STL class, if you remember, pushback just appends an element to our vector. Okay. So if I have say something like 0, 1, then after this our adjacency list will look like this is still empty, this is still empty, and this becomes 1. Of course, again, if it is undirected, then well, V is also adjacent to U, so then you will also have to insert U in the adjacency list of V. So in that case, it will end up looking like this. So this is what it looks like, the code for adjacency matrix and adjacency list. They are both very simple codes to implement. Okay, nothing too hard. Uh, does anyone require any clarifications on the code?
What if we are given multiple test cases?
If you're given multiple test cases, then in that case, you will have to, well, if you're using something like, okay, wait, I'll need a separate, need one more slide for this, just a moment, make one more slide. Hmm. Oh, oh, oops. Okay, yeah, so if you're given, if you're using something like while t minus minus, just for the sake of, you can just implement your graph. I mean, you can just put your graph inside here. Okay, just initialize it like this. Okay. Why is this G n plus 1 and int n comma m cn n comma nm, and then for int I equals 0, I less than m. So there is no additional trouble involved with multiple test cases as long you're doing as as long as you're doing everything inside your test case loop. If you have a
Okay, I was
global,
assuming global.
yeah. So if you have something global, let's say this whole thing you have outside, let's say uh, vector whatever G, if you have it here, then initially what you can do is that you can just run G dot clear. Uh, if, I think I covered this in the STL class, but G dot clear will just completely empty the adjacency list or matrix or whatever you're using. You'll make it completely empty, and then you will have to just wait. You'll have to do G dot resize n plus 1 like this. Okay. If you're using adjacency matrix, you will additionally have to go in and like for each int I equals 1, I less than equals n, I plus plus, you'll have to do g of I dot resize n plus 1. If you're using adjacency matrix, that is. If you're using adjacency list, there is no need for doing that. Uh, the point is that at the start of each test case, you completely empty G. And again, this will take linear time because, I mean, G was linear size to begin with. So there is no extra overhead associated with it. So, I mean, it will not break your time complexity in any way. So you cleared G, you resize G, and this will make just n plus 1 lists. So to n plus 1. Each of these lists will be empty, by the way. So that is why you'll, if you are using adjacency matrix, you'll have to go in, and for each list, you will have to resize them again to be n+1. And you can also pass n+1, 0 to additionally initialize each of these to 0. That's how you do it. And then you can just run your code as usual. That's how you do it. You understood what is going on?
Yeah, understood.
Yeah. Yeah. So you deal with it, and this is the code for it, and that completes a discussion. I mean, whatever I had planned for today, but since we still have more time, I think I can at least cover DFS. I think. So like, if anyone has any questions about whatever was taught so far today, they can ask right now. After this, I'll just discuss DFS. No one has any questions? I'll talk
Why do we
about.
use the like if we have adjacency list, then why do you need the matrix one?
Yeah, again, as I said, matrix has some uses. For example, in Floyd-Warshall algorithm, which is all pair shortest path algorithm. So for every pair of vertices, you want to find the shortest path. In that case, you can use a slightly modified form of adjacency matrix, and you can also use it to find number of walks of length k in O of n cube log k using matrix exponentiation. These are the two common use cases. This one runs in O of n cube, and this one runs in O of n cube log k. There are uses for adjacency matrix. It's not entirely useless. But yeah, you wouldn't be able to use it if n is very large. Yeah. So did I clear your doubt?
Yes.
Yeah. If you want after the class, you can just look up Floyd-Warshall and number of walks of length k problems. Okay. So, they are available. Mm. Okay, so I will just discuss depth first search. Didn't prepare the slides for it uh, because I didn't think I would finish it this early, but okay, so depth first search. There basically, if when we talk about how to like, okay, so far we have discussed about how to what is a graph and how to put the graph in a representation that is easy for us to use. Now the next thing is that how do you actually traverse the graph and like go through it? How to traverse the node with some order, or like if you want to, how to work with the graph. So this is achieved using graph traversals, of which there are two types. One is depth first search, and the other one that is there is breadth first search. Okay, so depth first search, what it does is explore uh, children first, and breadth first search is explore neighbors first. Uh, what each of these mean, I'll just come to in a bit. So by children, I just mean that you, from a given node, you go to the first node that you can find that is unvisited, and you just recurse into that node. Okay. So you're always going deep. Okay. So you're just like if you have a graph, like, I mean, I'm just providing a tree here for simplicity. So if you are at this node, you go to one of its children, but you not explore its neighbors. I mean, you go to one of his children, then from that child you go to a next child, and then from that child you go to a next child, and so on. You explore children first, and breadth first search is like you have this. So you first check each of these, all of every node that is adjacent to this node. Then for this node, you explore all the neighbors that are adjacent to this node. Then for this node, you explore all the neighbors that are adjacent to this node, and then you go on and on and on. Depth first search is implemented using a stack. I mean, usually we implement it as recursion, and recursion is basically nothing but, kind of an implicit stack. Behind the scenes, it's kind of stack only. And breadth first search is done using a queue. We have discussed both stack and queue in the STL class. So, uh, let's just look at how, like, let me just give a dry run, for example, on say this graph. So let's just take this graph. Okay, so this 1, 2, 3, 4, 5, oops, 2, 5, 6, then 7. Okay, so you have a stack. Yes, there's a stack. Okay, which is currently empty. Now we're going to start traversing from the first node. Okay, so in this stack, what we'll do is we'll push 1. Okay, so instead of drawing it like this, let me draw it like a bucket. Okay, so we have 1 in the bottom of the stack. Okay, so now what we'll do is we'll pop 1. Okay, we'll pop topmost. In this case, our topmost element is 1. So we'll just take 1 and push all neighbors of 1. Uh, of note is that you shouldn't push the neighbors. You shouldn't push all the neighbors. You should only push all unvisited neighbors. So you will have to keep a separate visited array, some visited array, which is like 1 if visited and 0 if not visited. So uh, only push those which have not yet been explored by you. Because, I mean, if you pushed some visited neighbor, again from that visited neighbor, you'd come back to the original node. So if you have, say, 1 and then you push 2, then from 2 you again push 1, then from 1 you again push 2, and then you'll be stuck in an infinite loop. So you should always push only the unvisited neighbors. Okay. So unvisited neighbors right now, so 1, okay, 1 we will mark as visited. So 1 is visited. Now we'll push, say, we popped 1. Now we push 2, and then we push 3, let's say. So now again, we will pop topmost. So we will take 3 out. So from 3, push all unvisited neighbors, which is 6. So we'll push 6. Again, okay, so first of all, we need to mark 3 as visited. Okay, so pop topmost, and then was one more step, mark visited, just to prevent from coming back to this node again in the future. Then from 3 you push 6, and then you again, is someone saying something? Okay, no mind. So again, pop topmost, you pop 6, mark it as visited, and then, well, you have completed. So next up you go to 2. So now you pop 2. So from 2, the unvisited neighbors are 4 and 5. So you push, say, I'm pushing in the order 5, 4. It's not guaranteed which order you'll push it in. It's not always 4, 5. So now you pop Now you push four. Now you pop four. Okay. From four you okay. Marker is visited. Then from four there's nothing to push. So next you pop five. So then from five you push seven. Marker is visited. And then from seven again you pop seven, and then there's nothing to pop from seven, and now you have visited everything. So you see, we always visited children first, and then we went to the next neighbor. And usually we do not use an explicit stack, but instead we implement it as a recursive function, which is to say like implement it like uh, uh, void DFS. And so then some int u, and then in this function we say we mark u as visited, and then for v in gu, where gu, if you remember, is the adjacency list of u. So adjacency list of u has uh all the vertices which are just adjacent to u. So so now for v in gu, if we have visited v, of course we will not push, just continue. But if you have not visited v, then we will call DFS again on v. Uh, so yeah, and then we'll just exit the function. This is how we implement DFS. If you want to implement using actual like explicit stack using stack int st, then you can also implement it without recursion. You know, by implementing as I told you, push and then pop. So if some stack, then stack dot push one, let's say, and then while the stack is not empty, when not stack dot empty, then you can just int u is equals to st dot top, and then you just pop it, and then you you know mark it as mark u as visited, and then push all unvisited neighbors. That's it. Also, I explained it for a tree, but you can apply the same thing on regular graphs. Just that you have to be careful if you are implementing like this. You have to check just in case that if u is also visited. If u is visited, then that's kind of redundant. If visu, then just continue. Just add this line just in case you're implementing like this. Otherwise, it's fine. Uh, this a slightly modified form of this code. I mean, if you want to say detect a cycle, if you want to find a cycle in a graph, or you want to find the number of connected components, you can just modify this code. Uh, I will, I will, okay. Hmm, okay, maybe I'll talk about how to find connected components using DFS, since we have still some more time left. Uh, why the proof of this, like why depth first search works in stack and breadth first search uses queue is uh, something that I cannot recall instantly, but just trust me on that. Uh, we'll talk more about it in the next class. So, any questions about how to like implement DFS at least? Like, no one has any problems with the recursive implementation, right? Okay, I think not. It seems not. So, let's just talk about how to find, say, connected components using this. Uh, so so to find connected components using DFS, if you have some graph, let's say that looks like, let's say like this. So, the point is that uh, inside the main function, like let's just uh, black box DFS as some function which will perform DFS for us. Now you go over each node for each node for each U. Uh, if U is if U is visited, then we do not need to do it again. Okay. Then DFS U, and then increment the count of connected components by 1. That's all you have to do. Why does this work? The reason is that if you start in some connected component, DFS will explore everything. It will not leave out any nodes, right? Because I mean, it's going to. uh, I mean, okay, just trust me on this, but DFS is going to end up exploring everything. If DFS explores everything in a connected component, if we start here, then we explore everything. In that case, that means all of these nodes have now been marked as visited, right? And that means we will never DFS from these nodes again. So we have succeeded in only counting this connected component exactly once, right? So for each connected component, we only want to increment CC by 1, and that can be achieved by just picking one node, incrementing the connected component count, and then just marking all nodes that are connected to it as visited. And that's why this works. Yeah, I was seeing someone saying something. Uh, I guess not.
Can you explain how we start this one? Like, uh,
Hmm?
I mean, like, okay, we are traversing all the connected dots. Now, how to start the search?
Oh, you can just go over nodes in any order and just call DFS if it's not visited. Just call the DFS function, and since DFS is implemented recursively, we are assuming it will just handle the rest for you. I mean, again, we are just assuming that we have a global G and visited array, a global adjacency list and visited array. Just we are assuming. Was that your question?
Uh, yeah, so we'll just start from each node once and we'll check the size. Is that it?
Yeah, I mean, you can keep track of size also. You will start from each node that has not already been visited.
Yes.
And yeah, yeah. So, mm, still have little more time, but I think we'll end the class early today. I don't think there's a point in covering more. I think I'll cover it when I'm better prepared. So for today, let's call it a day. The class is over. If you guys have anything else, you can leave. If you have questions, then please feel free to ask.
Thank you for the class.
You're welcome. Yeah, okay, then I'm ending the class. Okay, everyone, have a good day. I mean, good evening.